How is everyone? So I'm going to talk about property-based testing in SwiftCheck, or with SwiftCheck. And I didn't live in the UK. I've spent some time there, very little. How many of you are in tests and agree with this statement? Oh. Tests are so difficult that it all crashed. Hold on. All right, hopefully that won't happen again. Tests are so difficult to write, but they're not really difficult to write, are they? No, tests are not difficult to write. Tests cases are difficult to write. Why? Well, they're difficult because we have to think of everything that could go wrong, or every case that matters, every case that, and then we have to organize them in a way that when they fail, or when they succeed, we can read the tea leaves. I brought tea, just to answer Kate's question. And how many are enough? How many test cases do we have to write before we've satisfied our need to know that our code works? So, someone was supposed to ring a bell right about now, but it didn't happen. So how can we find test cases? That's what I'm here to tell you. I'm here to show you a way that we can just find test cases. Just let them come to us. I mean, yes, you can think of the ones that matter most, and then eventually you can say, every time I run, sometimes I find new problems, and they come to me. The first thing that we need to do is we actually need to just let randomness in. Can you let randomness into your life? Yeah? Yeah? Do you think, well, that was a pretty good laugh, but all right. Let's ask this again. Can you let randomness into your life? All right, okay. Yes. And when the test fails, can you reproduce that randomness? Can you say, oh, it was random, but now that I've found something that's interesting, I would actually like for this test to be repeated as it was. And then, in some cases, we would like to actually make our failing case a little simpler so that we can read it more easily. All right. Are you with me so far? Are you awake? Are you awake? Some of you, this side is awake. All of you. Just. All right, let's get testing. I have pretty simple type here, rational. And this type has a numerator and a denominator. Another word for this is a fraction or a ratio. And we would like to test this type. Hopefully nothing on this slide is jarring. Because if you're lost here, we're going to have a tough go of it. All right. So the first thing that we want to do is actually make something random. And again, I was supposed to get a bell right about now. He's not listening, but that's all right. So something random, we have a protocol named arbitrary. I want to just get a ratio or a int. I don't care which one, because this should work for everything in some sense. And arbitrary lets us conform to arbitrary and then give back a generator that will create instances of our type. You can see here that our arbitrary property just returns a generator for our type, and you say, yes, that's exactly what we return. What's a generator? Well, our generator returns arbitrary values. The randomness that it uses it receives a random number generator and a size. And it uses both of those things to control what goes in. This random number generator is used because then we can give numbers and reproduce failing test cases so we can figure out what actually went wrong. So we just return a generator of A being our type, the type that we're interested in. All right. Now that we have those two things, we can create random values. To do that, we need to conform to arbitrary. We conform to arbitrary by adding an arbitrary property, and the simplest way to actually return just a random thing is to use compose. Gen has a method named compose, and into the block that we pass in is passed a composer. And the composer is just a convenient way to call arbitrary on anything. It's kind of magic. Actually, it is magic. So this comp, you can see here we said comp generate, and we just did that twice. And all we're doing is passing in a random integer to our numerator and our denominator. We pass it in, and that's all we're doing right there. But our denominator should not be 0. It should not be 0, and we need a way to express that. And the way that we express that is using such that. Gen has a method where we can filter in typical functional fashion, and putting it all together, we get this busy slide. But you can see right there in the last long line that we're returning a random number and a random number that's not 0. How many people can hear that bell? All right, good. Otherwise, it's a little too random. All right, so we've set all of this stuff up, and we're wondering, what do we test? We can make random ratios. We can make random fractions. Great. Doesn't really help me. Properties. I said we're doing property-based testing. What's a property? I put properties on my types. How many people put properties on their types? Please, everyone, raise their hand. Because if you don't raise your hand at this point, you're just not listening. Right. Unfortunately, these are not those types of properties, right? These are different types of properties. There are two types of properties that make it easier to explain what I mean when I say properties. Round-trip properties are the easiest. A round-trip property is something where you go from one value to another value and then back to the original value. What do I mean? Well, if we took an int, made a string out of it by calling description, and then passed that into int, we should hopefully arrive back at the original int, if everything went well. That's it. It's not complicated. That's a round-trip property. Another round-trip property is this. If we have an array, and we reverse it, and then we reverse it again, what should we end up with? The original array. There are some flaws to this strategy. One of the flaws is that if you make the same mistake twice, say in your encoder and your decoder, well, I mean, it's not going to catch that. So if I encode in exactly the same wrong way that I decode, not going to be a problem. And if reverse just returned the original array like a jerk, then we're not going to catch that either. So maybe you need some other tests as well. And I'm sure you appreciate this ASCII art. Yeah, buddy. Yeah, buddy. Yes. Right? A commuting diagram property. This is similar to the round trip thing, but you say, oh, well, if I can get to the same place in two different ways, I should be able to test that I actually got to the same place. What do I mean? Well, if I have a base 64 encoder and Apple has a base 64 encoder, both of those encoders should end up with the same string. And so that's a commuting diagram property. Now, there are other types of properties. There's nothing saying that these are the only two types of things that you can test, but when I say property-based testing, these are properties that I'm talking about. Sort of truths about your program or the algorithms that you run. So they're properties in a more abstract sense than a property on a type. You know, it's what can I say in general about every time that I reverse an array? Well, if I do it twice, I have the same array. That's just a general truth based on describing what reverse should do. So, now that we have that out of the way, let's actually test some properties. I want to test addition. Anyone remember what commutativity is? Yeah? Wow, no one? Rough. This is gonna go bad. Well, the basic idea of commutativity is that if you reverse the arguments to addition, right? 1 plus 2 is the same as 2 plus 1. It makes sense when you say it out loud, but if your program does not respect this, something is wrong. And it's easy to miss this. It's easy to implement your method in some way where, that just doesn't happen because of an oversight. We can also test with 3 arguments. Same idea. It really shouldn't. I should mix this up even more and introduce some randomness. So what happens when your test fails? When your test fails, you will get this message. And you'll say, that's wonderful, but it's random, so when I ran it again, maybe it didn't run that exact same test. So, oh, well, that's the problem. So how do we capture that? Well, I want you, sir, could you remember that first number? You, could you remember the second one? And you remember that third number. All right? Is that the same number?
Yes.
He wrote it down. He cheated. I like you. Is that the same second number? He didn't write it down. He doesn't know. And you, sir, you have the hard one. It's the same number there. All right. All right. I'm glad you wrote that down. That's good. That's good. All right. So using this strategy, once you get the error, you catch it, and then you can actually have it replay that as many times as you need to figure out what the problem is. And then once you figured out the problem, you can decide, do you want to keep that random test, that not random test running, or would you like to just let randomness back into your life completely? When you choose to run your tests, it doesn't just keep going until the heat death of the universe. It does 100 or 150 or 50. You can decide how many random tests it will do every time you actually run. So the idea is that if you have continuous integration going, like using one of the partners, I believe it's Buddy Build or something like that, or bots, every time you run, it just takes 100 cases that it generates right then. And if you have those running every hour, that's 2,400 a day. Some of those would be the same because, yes, randomness, as we learned, has some repeating values. Now, this slide is not meant for you to actually read because that text is tiny. But you can see here in the fourth line that I'm still using assertions. They're still there. I can still use XC test to run boring, not random tests. And you can mix them up in the same methods, and you just have to use the property syntax for the properties that you actually want. We're not going to talk very much about shrinking, but there's one more method on arbitrary. Arbitrary. It's a funny word. Anyway. Shrink. And it's actually very important. So if you had an array with 2,000 elements and it failed, and then you got a test case back saying this failed, you would look at that 2,000 long array and you'd say, yes, it's very clear what's going wrong here. One person got the joke. Thank you. Shrinking says, all right, well, 2,000 failed. Is there a way that I can make this array smaller and still fail? So it takes out half the elements, and it says, do I still fail? All right, I failed, good, which is a funny thing to say. And it says, all right, 500 elements. Do I still fail? All right, good. All right. And hopefully it gets to a pretty manageable number. Maybe it gets to 20, and it says, do I still fail? 20. Oh, I didn't fail here, so then maybe it'll stop at 40 or whatever, right? The basic idea being, because we've introduced this randomness, we actually don't want to just accept every case. Not every value that not every type that we create will have a reasonable shrink. That's fine. Hopefully those types that you have that you can't shrink, you can read them. And if you can read them, we're good. But in every case that you can think of where you can actually shrink the value, please do. You're doing yourself a favor, especially for collections. Large collections, you want to shrink. But fortunately, SwiftCheck implements arbitrary and shrink for arrays, sets, dictionaries, all sorts of great stuff. So, what's the point of all this? You can spend less time writing tests, a little bit less time. You're still going to have to think through your tests. You're still going to have to spend time figuring out how to implement arbitrary and how to implement shrink. But the nice thing is, it pays off. Right? Hopefully, you'll get better tests out of this. No one said that you have to stop writing tests the old way. You just have a new way to write tests. In my opinion, you get easier diagnosis because as you fail in sort of these random cases, you get to see things that you didn't think of, which brings me to another point. In an earlier slide, we filtered out when the denominator was 0. Don't always filter out bad data. You can write a test case. If you can write a test case that accepts bad data and then does the correct thing, you can test that you do the correct thing. I just happen to know that there's really no reasonable way to accept 0 as the denominator for a fraction. So it crashes. Or, no, it doesn't exactly crash. And you should write test cases, right? You should write hard code test cases if you find a really sharp, edge case that you didn't capture in your properties. Write it down. There's absolutely no problem in using the replay arguments or just hard coding it and saying, I want to be sure that every time I run my tests, this crazy, crazy bug involving a gorilla happens over and over. Some of you are still listening. If you really like property-based testing, you're sold. How many people are sold? With your voices, please. Ooh, yeah. But you're still trapped in Objective-C. You can use, I shouldn't describe it like that. Objective-C is a wonderful language. It's a beautiful language. It's just not my favorite anymore, I'm sorry. Right. You can use Fox. And Fox is implemented in Objective-C, which gives us the ability, heard that one a little late, gives us the ability to actually use this in Objective-C and Swift. Downside being that you don't get the generics and all of that wonderful stuff, right? It's a little bit less pretty to look at. And with that, that's my time. Thank you very much. Hopefully you will all go out and download SwiftCheck or Fox.